Okay, so let us recall that in the previous video we discussed adherent points, which we will see eventually will be used in defining continuity of functions, continuity of real valued functions. But that is not the only kind of point we will need. We will need another type of, actually two or three more types of points. One of them is the notion of limit points or cluster points, which are related to adherent points, but they are a different notion. Just like what I said right now, that adherent points will eventually be used in defining continuity of functions. Limit points, just like that, will be used in defining differentiation of functions. Okay, that will come in the next chapter. So let's see this new thing. This is definition item number 18. Limit points. So this is how the definition goes. Let x be a subset of the set of real numbers and small x be a real number. We say small x is a limit point, or it has another name, cluster point of capital X if small x is an adherent point of this set. So you can see that a limit point or cluster point is after all an adherent point again, but not of the set itself, but this subset of x that you obtain when you remove this point x from x. Note that just like what we had in the definition of an adherent point, the point itself may not actually be an element of x. It may be, it may not be. Okay, so both the possibilities are there. And x being an adherent point of this also, of course, just simply means this, that x belongs to the closure of this set. So let me just repeat. X is a limit point or cluster point of our set if it is an adherent point of this subset. That's it. Now if you use the actual definition of an adherent point, then you can rephrase this whole thing using epsilon and all those things like this. That is, x is a limit point of x if and only if for every epsilon greater than 0. So what should it be? X is an adherent point of this. So for every epsilon greater than 0, there must be a point from here that is epsilon close to x, because that's the meaning of an adherent point. There exists a y in this set, or we can write like this, a y in x such that y is different from x and y is epsilon close to x, that is their distance is at most epsilon, it cannot be beyond epsilon. So you can see clearly that the difference between an ordinary adherent point and a limit point is that in case of an adherent point, any region around x, because this epsilon determines a region around x, has to just contain a point of x. In case of limit point, however, such a region has to contain again a point of x, but other than the point itself, other than that x itself. Okay, so that is the notion of a limit point or a cluster point. And there is another type of points that is also included in this definition, namely isolated points. We say some other types of points will also come eventually, but not right now. We say x is an isolated point of our set if x belongs to x and there exists epsilon greater than 0 such that I don't want to clean and wrap this up fully right now itself, such that just want to show the distinction between these two types of points, between their conditions. So if I use loose terms, okay, not rigorous actual standard terms, if I use loose terms, it just simply means this. Say you have your set x. Of course, your x actually doesn't look like this, it's a subset of the real line, but let's just assume that this is the Venn diagram of x. And you have R, okay, outside. A point x is said to be a limit point or a cluster point of x if there is some if every region around x contains at least one point y of x that is different from x itself. Every region, and that every region corresponds to something happening for every epsilon. Epsilon is the radius of that region, this region, radius. After all, in our case, these things are just open intervals on R. But we will see that these ideas have their extensions later on. So that's why I am drawing these figures. So you can just simply, somewhat vaguely imagine that this x is a point somewhere in some sort of space, and this capital X is a subset of that space. Then this is a cluster point or a limit point if elements of X cluster around this point. No matter what region you choose around X, you will always find at least one point of X inside that region, which is different from X itself. However, let us now concentrate on this other notion of isolated points. A point X is said to be an isolated point of X if, first of all, X is an element of X. That is not necessary for a limit point. A limit point may be an element of X, may not be an element of X. Both the possibilities are there. I have already said so. However, the situation of an isolated point is like this. Small x will be an isolated point of X if, first of all, it is inside X. Okay, so that is one condition. And what about this thing? It just says that, okay, so this is the region around x given by epsilon. Do you see the difference? Here we have the quantifier for every, but here we have for some, or there exists. So here in case of isolated point, there exists a region, at least one region around x, so that if you consider the intersection of x and that region, then that intersection is this singleton set consisting of x only. In other words, within this region there is nothing from x other than the point x itself. That's why it is isolated, it's alone. Okay, the name also suggests that. So that is the difference between a limit point and an isolated point. And we will see, it is coming, that if we are given a set x in R, then every adherent point of x is actually either a limit point or an isolated point. Okay, and of course not both at the same time, because they have the exact opposite nature. No, you can say that limit points are popular in x. Elements of x cluster around a limit point, but an isolated point, although it's a point in x itself, but it is highly unpopular. There is a region that beyond, within that region you won't find any element of the set x other than the point itself. And now to illustrate these things, there is an example. So this is item number 19. Consider the set X, which is the union of the open interval 1, 2 and the singleton set 3. Now before seeing what the author is saying about this set, let's just draw the set on the real line, so that we can see in front of our very eyes what is going on. So this is our 1 and this is 2 and so this is 3, and let me just extend this a little bit more on that side. So the remarks the author made about this set is this: 3 is an adherent point of x, simply because 3 is a point of x. We have already seen that every point of a set is its adherent point, but there may be others also outside. Okay, so 3 is an adherent point of x, but it's not a limit point. To see why that is the case, for 3 to be a limit point, 3 should be popular. But is 3 popular? No. Actually 3 is sitting alone, right? In the sense that near 3 there is no element of the set other than 3 itself. They are somewhat far away from 3. If you want to be rigorous, it just means that there exists a region around 3 that which is given by some epsilon. To be specific, you can just take epsilon to be, say, 1/2. Okay, so this will be, that is, you can consider this closed interval 2.5 and 3.5. 2.5 is 3 minus 0.5 and 3.5 is 3 plus 0.5. So 0.5 is your epsilon. Then this is your x. Your x is it consists of all the points lying between 1 and 2, excluding 1 and 2 of course, and the point 3. So this intersection of x with that neighborhood of 3 is just the singleton set 3. So that's why 3 is an isolated point, it's not a limit point. Instead, 3 is an isolated point. On the other hand, if one looks at 2, you keep in mind that for an isolated point, we just need one neighborhood around that point in which the point is alone, in the sense that there is nothing else from the set around that point. But to show that a point is a limit point, every neighborhood has to be seen, okay, has to be checked. 2 is a limit point. Two is a limit point of x, and 2 is definitely not an isolated point. To see how 2 is a limit point, again without being too specific, you just take any neighborhood of 2, say given by some epsilon which is fairly small, so that around 2 you have only that much space. So what do you need to show that 2 is a limit point? A point from x that lies within that region, but which is not equal to 2. And you can see that all because x is this much and this. So all those points that you need from x can be chosen from the left side of 2, from there. And you can clearly see, geometrically at least, that no matter how small your epsilon is, you always get something to the left of 2, so that that thing is different from 2 of course, but it lies within that region. So that's why 2 is a limit point. And you can also, because of this fact, see that 2 is not an isolated point. Although 2 is not an isolated point. So there is a kind of, what you can say, a kind of, I forgot the word. You can understand what I am trying to say. A point is either going to be a limit point or an isolated, an adherent point of course of the set, because both 3 and 2 are adherent points, but in their own ways, and those ways are different. 3 is adherent simply because 3 is an element of the set. 2 is adherent because 2 is not an element of the set but is very close to the set. And we will actually prove later on that this is the case, namely the set of all isolated points and the set of all limit points of a given set precisely give the set of all adherent points, or in other words, the closure of the set. And clearly from the definition, it immediately follows, almost immediately, that limit points and isolated points are totally different things. They cannot both be, they cannot occur simultaneously. Okay, now we also know the sequential formulation of an adherent point. Do you remember that? A point x is said to be an adherent point of x or in other words lies in the closure of X if and only if there exists a sequence of elements in X that converges to that point. So using this criterion, we can now reformulate the notion of limit points also, because after all they are by definition of an adherent point. So that is the next remark. And that result was what lemma 9114 here. By lemma 9114, we see that X is a limit point of X if and only if there exists a sequence in that subset X minus X, X difference X, that converges to this small x. So, in other words, there exists such a sequence in capital X, all of whose terms are different from small x, and that converges to small x. If this happens, then small x is a limit point of X, and conversely, if small x is a limit point of X, then such a sequence exists. Now here in the next result, it's a lemma. For some known sets, their limit points have been calculated. If I is an interval in R, possibly infinite, i.e., well, there was no need to write, but the author has written I is this or this or this or this or an infinite interval like this. Then every point of I is a limit point of I. I don't know why the entire set of real numbers has been ignored here in this list, because for that also every point is a limit point. The author has chosen to handle only this case, namely the author has taken I as only the closed interval. And I'm also going to give just a hint of the proof. It's already there in the text. And let x be an element of I. Then there are three cases. Actually there are infinitely many cases, but three main cases. X can be A, or X can satisfy these inequalities, or X can be B. Okay. Now, since we have, according to the previous remark, a sequential formulation of the notion of limit points, so we can just apply that to show that, for example, you take up this one, to show that A is the limit point of I, you just need a sequence of elements in I, all of whose terms are different from A, and that converges to A. That's it. And to find such a sequence, you can do this. Consider the sequence so you can understand that what I am writing is really not a proof, it's only a hint. Consider the sequence A plus 1 over n, where n varies from n to infinity in A comma B, that is I, same thing. But what is this n, capital N, where capital N is a natural number such that A plus 1 over n is less than or equal to B for all n greater than or equal to capital N. Is it possible to have such an n regardless of what A and B are? Yes. How? Let us just see. Note that although it has not been mentioned, right, that A is less than B, but we are assuming that A is less than B. What would happen if A is greater than or equal to B, suppose? Or say A is greater than B. In that case, this interval would be the empty set. But I think nothing has been mentioned here about A and B, because do you recall in one remark where we defined intervals themselves? After that, we, I think, had a remark where it was decided that we are not going to consider degenerate intervals, which come under the definition of intervals itself, but they turn out to either be singleton sets or empty sets. So we won't consider them. So that's why here it is assumed that A is less than or equal to B, so that this has at least one point. So because A is less than O, and also we are not considering A equal to B, because then again we will get a degenerate interval. So actually A is less than B, which means what? It means that B minus A is the positive real number. Now, from the Archimedean principle, one can easily prove that a large enough n can be chosen such that, oh, there is that problem now, n should not be 0. So you can assume this n to be coming from the set of all positive integers. We are just removing 0 from the set of natural numbers. So there is a large enough positive integer n such that 1 over n will be less than b minus a. But then what are we getting? This implies a plus 1 over n is less than b. But at the same time, if you are considering this type of natural numbers, small n greater than or equal to n, then 1 over n will be less than or equal to 1 over n naturally from properties of inequality. In other words, for such n, a plus 1 over n will be less than or equal to a plus 1 over capital N, which will be less than b. But at the same time, because 1 over n, no matter how small, is a positive real number, so this is greater than a. So you see that all of these real numbers, which are the terms of our sequence, lie between a and b, and that's why they belong to I. But of course, you have to choose this starting index carefully so that this actually happens. And once it happens, after that point onwards, it continues to happen. So this is actually a sequence in I, but at the same time, this sequence is different from A in the sense that all of its terms are different from A. For no n will this ever be equal to A. And finally, the limit of this sequence, of course, is nothing but A. So by the previous remark, A is a limit point of I. Similarly, B is a limit point of I. In case of B, you have to consider a sequence like this. This will make the terms of the sequence less than b, but at the same time they have to be greater than a. So that's to adjust that, you have to choose this n prime, again some positive integer, carefully. And similar arguments would show that x is a limit point if it lies strictly between a and b. In case of such an x, you can choose to have a sequence that lies to the left of x, or a sequence like this that lies to the right of x. That is your choice. And the other cases, that is I being the other types of intervals, are of course similar. Okay, so that is a kind of a, it's not, I can't say it's a proof, but it's an elaborate hint of an actual complete proof. And finally, let us just see another definition, so that using it, next Sunday we can see something new and something really important. I will say what it will be. It has a name, it's called the Hein-Borel theorem. It is so important that once we state and prove it, we will continue to use it throughout the book. So the next definition is that of bounded sets. Bounded sets. A set X, again a subset of R, is said to be bounded if X is contained in a closed interval of this form for some real number m that is positive. a pretty straightforward definition and something that you already know, okay, or you feel like this is what boundedness should be. It is natural, I am saying, because x is being bounded from below by minus m and from above by m. That's why minus m is going to be a lower bound of x, and m is going to be an upper bound of x. And there is an example to illustrate even this. With this example, we are going to end this video. So without writing too much, I will just simply say what the author has said in the example. So what he says is that if you have two real numbers a and b with a less than b, then the closed interval a comma b is bounded. Because it is contained in such a closed interval. Well, you can just simply say that the closed interval can itself be taken as the closed interval, but this may not have this specific form. A may not be minus b, okay, in general, where so we may have to in general take a larger interval. Note that there is a difference between a general interval like this and an interval of this kind. A general interval is just an interval, whereas this interval has 0 as its midpoint, where the author says that this value of m will work. How exactly, I leave that to you. But you can at least see one thing, that this m has to be greater than 0. Do you see why? One thing is immediately clear, that since we are calculating the maximum of two absolute values, so m has to be greater than or equal to 0, because the absolute value of any real number is non-negative. However, why is m greater than 0 though? Is it not possible for both of them to be equal to 0, so that the maximum is 0? No, because if both of them are equal to 0, then a and b are both 0, but that will contradict this inequality because they are not equal. Okay, so that's why m at least is greater than 0. But with this m, why is this a subset of this, that I leave to you to verify. However, this, for example, is not bounded, or which we also say unbounded. To prove why that is so, you can use the Archimedean principle. Now, before I end this video, let me just at least say what that result is all about. That I said just now is going to be very important. It is this. Let me give you two statements, okay. Suppose that x is a subset of R. The first statement is this: x is closed and bounded. Do you remember closed? X is closed if it equals its own closure, or in other words, if it contains all of its adherent points. And we have just now seen what boundedness is. So say x is closed and bounded. And there is another statement: every sequence of elements in X, which let me express shortly by saying every sequence an in X has a convergent subsequence ANI, which converges to a point inside X, that is this. Such that the limit of this subsequence is in X. So what this second statement is saying is that no matter what sequence you choose in X, it's not about there exists a sequence AN. No, for every sequence AN in X, it has a subsequence that converges to a point inside X. So what the theorem is going to say, that we will see next Sunday, is that these two statements are equivalent. That is, X is closed and bounded if and only if such a thing happens. And this is so powerful, this result, that we will use it again and again in many places. We will continue to use it throughout analysis. It's known as Heine-Borel theorem, named after its contributors. So we will see about these things in next Sunday. So let me just stop the video here itself, and our next upload is this coming Tuesday. And I don't know if you have noticed or not, I have changed some things. Instead of making videos about solutions to exercise problems, I have decided to provide those solutions in the form of community posts. So please let me know if you are okay with that. For some videos I can't do that. For example, for analysis I can't do this because one of my viewers has some problem reading small texts. Okay, so if you have some such problem, please let me know. Otherwise I will just continue to make community posts which will be solutions to exercise problems. But for theory parts like this, discussion, examples, corollaries, theorems, I will continue to make usual videos. Okay, so please let me know about that. So, okay, so next Tuesday, what are we going to do? Field, field, we have already gone through that once more. Tuesday, let's do vector spaces. And vector spaces means right now we are solving problems, right? If that is the case, then I will just you will just see a community post about some other solutions of the subsequent problems that should occur in a video, but I'm not going to make a video. So if you are opposing to that, please let me know. Okay, so anyway, see you on Tuesday in a community post. You won't see me, of course. And that's just it for tonight. So until next time, this is me, Lucifer, from A Mathematical Room. Have a nice night.